Hello, everyone. My name is Wei-Han Lien, 电 Wei-Han. 我台湾生的，所以 I'm really glad back to Taiwan. So definitely ask me like if I want to sponsor RISC-V Taipei. I said for sure. Why not? It's my hometown, right? So today I'm going to talk about the empower AI innovation with the versatile and open source RISC-V processor. So versatility actually coming from this open source standard as well. So it's actually tightly coupled together in terms of its property. So I will talk about that. So this is exciting period of the time in the human history, right? So my wife asked me why I work so long, why I'm so enthusiastic about what I'm working. So my career has been working on x86 early on when I graduated from school, and then I'm working on Apple, iPhone, iPad phone chips, right? I've been working there for 13 years. And then all of this product is actually great, right? iPhone is revolutionized thing, but this is bigger, even bigger. I just tell my wife saying that this is an interesting human history of the time that 100 years later, people will identify this as a new industrial age where the machine intelligence replaces the human intellect. It's how important that is, right? So AI will change everything we are doing in the next 10 years, right? From how we do business, how we interact with the people, and how we actually live, right? The one special attribute of the AI is actually coming from this personalization, right? So what it does is actually allow the technology create this intimacy to you in terms of usage of the technology. So you can personalize your drug when you have a disease. You can personalize what your kids learn in the classes, right, based on their level and their interest. So this personalization, right, requires tons of compute, right? So this is why today everybody is trying to do solving this computation problem, because the coupling of the computation requirement and also the personalization, there's 50 billion of the people, is tremendous amount of computation requirement. So so to do this customized digital transformation I just talked about through the AI, so what I want to talk about is, so what exactly is the computation requirement? You can see in this chart, right? I've been showing this many times. I find it interesting is that since 2012, the AI complexity computation requirement is characterized by its model parameter size has been doubled every 3 months, right? So this exponential growth on the computation need, and this coupling also about the computation data generated by the human race every day is 2.5 quadrillion bytes per day. This collide together generated the perfect storm for the computation requirement in the AI, right? So our view, my view of this solving this computation problem requirement is that you have to go through AI computation everywhere. That means the computation hierarchy, right, you are using daily, which I will present next, is required to be doing all the level of different AI you have. So the AI revolution, right, has to be pervasive in terms of computation. That means on the client device, right, on the edge device, on the data center, you all need AI, but it's impossible to send all the data to the data center. The computation has to be distributed, right, separated, partitioned, enable the efficient access, right? I constantly giving this analogy about, like, if the human body actually send all the neuron signal from the body to your brain, your neuron will be so big that it's impossible to handle that efficiently in terms of transmission. Human being is the most power efficient processing engine in the world. 100,000 years, millions of years optimize how you actually operate, give you the best actually power efficiency, right? So it's a distributed processing, right? So that's why Tenstorrent is building this we call scalable technology, enable you to build the computation, AI computation, all the way from client device to the computation hierarchy to the data center, right? So this is kind of demonstrating this picture here, right? So the key component we are actually building, the scalable technology is the CPU, right, which is based on the RISC-V, we're building high performance scalable RISC-V technology. And then we also have scalable AI. And to further that, we actually now start building the chip-based system so you can have this flexibility on the composition and also scalability in terms of computation. So now we got to the main topic, right? So you understand that the computation requirement that we need to have the scalable computation to address the AI computation. And then why the RISC-V is actually very suitable for addressing this need. Right? So you look on RISC-V, it's an open standard. The open standard actually creates versatility, right? You need it for addressing the AI compute. Like I mentioned, the AIs have to be compute on all the compute hierarchy you use every day. So RISC-V has this scalability, right? So you can basically, without license, building any arbitrary PPA performance level, big, small processor need for AI processing in different level, right? Secondly is that extensibility is that vertically, you're building a processor in a particular element, you're able to extend the ISA semantics to support, to accelerate particular function you're actually interested in doing, right? So that's the flexible extensibility horizontally, right? Efficiency, from my perspective, I've been working on 4 different ISA. RISC-V coming later, in general, it has less historical baggage in terms of ISA support to support the compatibility. So you will be able to building a little bit more efficient processing, computation. And last one is actually the stability. I think this is very important as well, right? What I mean stable is that the user of the technology can choose whatever vendor or building their own technology by themselves, right? So the stable supply of technology is important for this very ever-changing industry because the demand is so dynamic, right? So you need a lot of vendors supplying the solution you have. And also, if you have the capability like Tenstorrent, we are building our own solution to supporting the AI. So this 4 properties is actually very, very important why there are so many companies choosing the RISC-V, right, to supporting their AI. I think the open standard actually enable this wide variety of the product you actually can build. So that's a good thing. So Tenstorrent RISC-V technology have been working with the ecosystem partner, right? So we are going after, so you look on our ecosystem, our partner, right? We can go to auto space, we can go to data center. We are primarily focused on the company, focused on the data center. We also have a client partnership. So it manifests itself, the technology we are building, the scalable technology is actually going to all level computation hierarchy we're using every day. And then talk about the ecosystem, the potential of the supply chain issue that the other company using like on architecture, x86 architecture, right? So you have more than 10, 20, or even 30 companies provide the RISC-V IP now. This stability of the supply chain, right? One company ceases to use this, or you go for the better option, right? It's such a wonderful thing for building the AI computer. So back to before I dive in, actually how Tenstorrent using the RISC-V for our AI technology, I want to give you a little bit background on our product so you understand it. Company is leading by legendary architect Jim Keller, right? So if you know Jim Keller, he's been working on digital alpha. He has been in Apple creating the A-series processor, in AMD inventing Zen, in Tesla inventing the Hardware 3, right? Autonomous driving system, he started that. So now he's our CEO, right? I've been having a working relationship for him for 20 years. The 3 technology we are keep building is that we are sharply focused on data center technology, competing with NVIDIA, right? So we are building AI technology, right, based on our Tensx IP, and then we're also building the Ascon CPU, high-performance CPU, 18 to 20 spec in processor, right? And then using that technology for building a heterogeneous computing system. Of course, the AI is tremendously important in terms of the software stack. So we have the Medallion stack and Buddha stack, right? So that's the 2 stack we have. And then we use the technology, we also license our technology, right? The key important thing to win this AI war with this NVIDIA big giant is actually cooperation among the industry, right? With the open standard, open source. So Tenstorrent is interesting. We open source our AI software stack everywhere. You can download it, play with it, right? And then we also plan maybe in the future open our hardware standard as well. And then RISC-V processor we're building is already standard, and the ecosystem we're actually building a chiplet ecosystem, right, is also very, very good. That's why we can address our product with the data center, with the autonomous industry, and then client device. So this is the company actually has a partnership engagement with us, ranging from multi-super billion dollar like Samsung, LG, Hynix, right? All this company and Hyundai, right? And also like Bosch, right? All the company we're actually involved with is actually like our technology because it's open and it's also addressing the computation need in the AI market. So kind of re-talk about it, right? So we have two IP, one is high performance RISC-V, one is Tenstorrent IP is a fundamental building block, scalable building block for our AI architecture, right? We have an AI chip that we're building the chip that technology. We're going to tape out, Q1 next year, we're going to tape out many different chipsets so that we can compose them together. And then we're also building our own server as well, right? So we're building a server box, which is contain 32 of the AI accelerator competing with DGX, right, in NVIDIA offering. Right? We also have all open source software, right? Software is tremendously important. We are open source, we are collecting, we are having our partner co-developing the software stack. So this is our roadmap, right? So giving just briefly overview of the roadmap, right? So we already have a Grayscale, we have Wei-Han, it's actually selling, right? So we're building workstation, we're building data center box, then Blackhole is being bring up, right? We'll be shipping end of the year based on TSMC and N6 technology. It's also the first technology actually having the heterogeneous compute. That's going to have an AI accelerator. We also have a general purpose compute in a one single die. So I'm leading the next generation definition on Grendel, right? So it's a chiplet ecosystem. So you have the Quasar, which is our next generation AI computation die, and also the Aegis, which is the next generation high performance CPU server, right? So based on the RISC-V architecture. So all these two technology can compose together in any kind of configuration, right, to address the computation need in the data center. So we have two software stack. Buddha is a software stack, it's a compiler driven. So you can write PyTorch, you compile and map to the hardware, right? So it's an automatic flow, easier for developers not familiar with the software stack, right? And write it and want to test their algorithm correctness, right? Less performant, but we also have the medallion flow, which is basically the bottom-up approach, right? Based on the library, you can customize it. If you're familiar with the hardware, right, you can super optimize it. So how we actually, so I gave you a kind of a brief technology roadmap introduction about Tenstorrent technology. So I want to talk about how we exactly using the RISC-V open standard processor, right, in our technology. So you can see that on the right, on the left-hand side is our IP. So you can see that little T element we call Tensix. It's actually the basic building block for our AI accelerator. Inside that Tensix, right, we can use a lot of Tensix, compose it together to building a larger AI compute, right? So you connect to the NOC, right? The NOC topology can everything you choose, well, whatever you choose to build. But in our case, we build in mesh, right? So mesh topology, 2D mesh technology. So we're using the IP, we can instantiate it, we can sell to the people, and we have partner instantiate in there like television, for example, right? And using our IP. But also we instantiate a lot and building the chiplet, right, for the next generation. So it contains many Tensix in there and connect to the mesh and forming a computation, basic computation platform. Then we take the chiplet and compose it together and make it even bigger compute, right? Putting it in a package. So this is a scalable architecture. Like I mentioned, it's very important for you when you address the computation need in AI, you have the scalable solution because the computation has to happen everywhere, right? And then our system chiplet has a scalable technology based on the Ethernet. So you can connect multiple of them, forming this we call Galaxy box. Is using to competing with the NVIDIA GDX box. So this is how we actually has the scalable solution all of it one tiny 10.6 element, putting in IP, embedded IoT space, or going to all the way to data center. Right, so this is just a logical view, right? So you can see the 10.6 there, right? That's a building block, right? There's a tiny little RISC-V processor where I explained to you how we actually use them and compose them into the NOC and then forming a larger compute, and eventually we use that using the Ethernet, technology to expand it, doing the scale and scale up. And then we can build in this galaxy box. In each of the boxes here, you see in the middle, it's actually 32 processors in there, right? So we can use that and connect them and then form even a larger compute. So this scalable 10x element here, you can see that there's two distinct elements. One is the communication on the left-hand right-hand side, using to receive the data, right? In the middle, there's a computation units to issue the instruction to the matrix engine. So it's a specialized MIMD, multi-instruction, multi-data stream, distributed processing. And coordination is through the RISC-V standard instruction, right, to lock in the semantics to communicate each cell. It's like a multi-MPI interface, right? So in the middle, there's the processor is responsible for issue the instruction, manages traffic, going to the scratchpad memory, right? So you can issue the instruction to the vector and matrix engine. And then in the middle, in the two on the side, is basically RISC-V processor using to packing and unpacking the data sending from the NOC. And we also have a distinct communication subsystem using for managing NOC, receiving the package, right? And manage the FIFO on the input and output side, and communicate with the other 10x unit, right, through the NOC in the other computation area. So the process I just talked about, the usage is many very small embedded processor, right? They have specialized function, they have a special usage, they are dedicated to one with the work. They can potentially using for general purpose compute, like sometimes we call in-packet, in-communication compute. But in general, that's not the primary usage because they're less efficient in terms of its computation capability. Right. However, it's a really good control process to control how you issue instruction to the accelerator. And we are building this high-performance CPU, which you see there. We're in the process of the taping out. The Q1 will tape out, and this is running great in the emulation. We are performance correlated at the 18 spec-in. We plan to going up to 20 spec-in per gigahertz. So if anyone interested to license this core, let me know. Yeah. And then we plan to use the CPU as a whole CPU, replacing the x86 in our data center, right? So currently we are buying very expensive x86 processor as a whole CPU, but we are planning to replace all the x86 CPU in our system, right, without the ASCOM. We also plan to use this CPU processor as a part of the acceleration, right? So some of the computation not doing well by the accelerator, we are actually using our RISC-V CPU to offloading that computation. Right? So this is actually how we actually plan to use this as well. Whole CPU function and also some of the acceleration function with the vector units. The chiplet system, like in the future, like you can see, this is one example of how we compose a chiplet system. We have AI chiplet, we have CPU chiplet on the top, we have the memory chiplet on the side, right, GDDR interface, and the bottom we have I/O scale in the chiplet system. So in the future, this heterogeneous compute is actually very important, right? So symbolic AI coupled with a sub-symbolic AI in the future is actually important AI model in train. Currently, the sub-symbolic computation is not predictable, it's not secure. For example, you're sending some information that it might be give you a probabilistic, very bad result, right? So it's not safe at all. So for the future generation, AI safety is actually the primary choice, then symbolic AI is the way to go, right? So this coupling between sub-symbolic and symbolic AI is the trend, and our heterogeneous platform is there to solving that problem. So summary, this is kind of funny, right? Wow, AI is such a big market, it's so complex, but you look on AI model is just 600 lines of code, right? You can download our code on GitHub, Llama. It's only 600 lines. But it's a tremendous amount of data you have to process, right? And the complexity of managing this tremendous data and cooperating together, coordinate together is very, very complex, right? So you need DPU, you need GPU, you need CPU. So this is just kind of break it down, right? So how the RISC-V can run in our AI software stack. You can see that it's a hierarchical partition and going from a couple hundred processors growing to a couple thousand processors, right? 64,000 processors. So that complexity layer by layer of the software running in there coordinate perfectly to achieve the performance very performs really, really well based on all the data movement, very, very complex. That's why everybody is struggling about this problem. Okay, my time is up. So why the RISC-V is actually important, right? So I want to emphasize its scalability, extensibility, efficiency, and also its stability, right? That's why the RISC-V is actually the choice for the AI development in the future, and Tenstorrent is using that for developing our AI platform. Thank you.